All right, everybody. Can you guys hear me all right? Hoping so. Is the mic on and working? Wonderful. Thank you for letting me know, Jennifer. Again, with all these review sessions, is there anybody that is uncomfortable having their name recorded in the video? Again, I like to record the videos with the chat so everyone can see the chat. Unfortunately, your name appears in the chat, so is there anyone with a problem with this? If you do have a problem, that's okay. Just let me know, and I can edit it out later. But again, all you have to do is just let me know, okay? How are you guys doing? You guys as tired as me? It's been a long week, and I say that, but I'm sure that you guys have had an even longer week, so let me just apologize on behalf of the department. I know that you guys are really getting it right now, and yeah, I'm sorry for that. I know in third and fourth year it could be a lot, but the good news is reading week is almost here. The only thing really in your way, from what I've heard in today's lecture, is my own midterm for 398. But as we are going to see through the exam reviews, it's not going to be too bad. Midterm 1, it could have been really bad because when we're dealing with linear algebra, there is a lot of tricks to it. There's tricks everywhere. When we actually start dealing with physically possible scenarios like we have in this midterm, there's not as many tricks really. It's all more calculation based, which I think students prefer. So hopefully you guys find this exam much easier. Before we begin, does anybody have any questions about anything, or are we basically ready to start? All right, I'm going to take no questions again. If you guys have any questions, just throw them into Zoom chat. I'm happy to answer anything that you guys might have. And we will begin. Okay? So we're going to scroll down. This is the 2015 midterm. This comes from Dr. Sammer. And it's essentially what we would have had if we did midterms in person. Now, for those of you who were at the review session yesterday, you guys remember that Dr. Sammer's midterms were cumulative, meaning that he tested a lot of topics from the first part of the course. I said that I'm not testing these topics, and in order to save time, we are going to skip over them in this review session. I'm going to post the PDF of the complete solution, so with every question answered. So if you guys are interested in these types of questions, it will be available on the PDF. But in order to save time, because I'm tired, I know that you guys are tired, we are going to skip over them. So if we were to look here, the first three questions are basically what we covered before topic 3, before we talked about strain. So this right here, question 1, this will not be tested on the midterm. This is a cross-product identity. Question number 2 deals with symmetric matrices. So this will also not be on our midterm. And then finally, question 3 here is basically asking if a function is surjective, injective, or bijective. Again, this will not be on our midterm. If you guys are curious about the answers or how I solved it, again, I will put the complete solution PDF on eClass after we're done our review session here. So let's go to question 4. Question 4 in 2015 is the first real question that you guys could potentially see on the midterm that I give you. As we can see, we have a cylinder and we are applying a lot of stresses to our cylinder. So of course, if we have stress, this is a topic that we've covered more recently, so it is fair game. The question itself says the shown figure represents a specimen under a confined compression test. So as we can see, we have compression in every direction. And when I have these, I personally, and you guys don't have to do these, but I like to define a coordinate system. So what I'm going, I don't know why that popped over to the side. We are going to define a coordinate system just to help us recognize where our stresses are. So for vertical, I like to put this as E2. For confinement, or the lateral directions, I call them E1 and E3, just like that. So it says the material is linear elastic isotropic with a Young's modulus of 2 GPa and a Poissons ratio of 0. The original diameter and length of the specimen before the pressures were 20 and 100 millimeters respectively, and after slowly increasing the pressure until failure, the material failed with a final diameter and length of 18 and 80 millimeters respectively. And all the question wants is the maximum shear stress. So what is the maximum shear stress at failure? So if we want maximum shear stress, or if we even want von Mises shear stress, or not von Mises shear stress, just von Mises stress, we need to start figuring out what our stress components are. If we look at the actual diagram, it just says that we have a bunch of pressure. It doesn't give us any values. The only thing the question really gives us is a bunch of displacements. We can see how much our cylinder expanded and contracted in both the E1/E3 direction as well as the E2 direction. So we have some things going for us. The first thing that we have going for us is that the Poissons ratio is equal to 0. This simplifies almost every single one of our calculations. Let's go over to the equation if I wanted epsilon 1,1. If I wanted epsilon 1,1 for a linear elastic material, we know it's going to be sigma 1,1 divided by E minus nu times sigma 2,2 divided by E minus nu times sigma 3,3 divided by E. Now, since our Poissons ratio is equal to 0, these two terms cancel out. And as we are going to see, it becomes very nice because our relationship between stress and strain for all three of these, or all three directions, is going to be just that first term. So epsilon 2,2, well, that's just going to be sigma 2,2 divided by E. And then finally, epsilon 3,3. This is going to be sigma 3,3 divided by E. So as we can see, we can find our three stress components, sigma 1,1, 2,2, and 3,3, if we know the strains. And the key to finding the strains is that we know the lengths, or the dimensions, before the deformation, and we know the dimensions after deformation. So basically, we said kind of in the last video that if I wanted a length, its current length, it's going to be its original length multiplied by 1 plus epsilon. Now what I can do is I can modify this formula and say that epsilon, the strain, is going to be equal to L divided by L naught minus 1. So this is great because since I know my length before and after deformation, I can find the strain in each direction. So we're going to start off with epsilon 1,1, and we know that this is going to be the same as epsilon 3,3 because it's both in that diameter, the diameter direction. So this is going to be the diameter after deformation, which we have as 18, divided by the diameter before deformation, which is 20, and then minus 1. As we are going to see, once we substitute that in, we get a strain of negative 0.1. Epsilon 2,2, it's going to be the same process, but now we are looking at kind of the height of the cylinder. So we know it starts at 100 and it goes down to 80. So we're going to have 80 divided by 100 minus 1, and we find that epsilon 2,2 in this particular case is just going to be negative 0.2. So now that we have all three strain components, epsilon 1,1, 2,2, and 3,3, we can use our formula we have on the left-hand side to figure out our stress components. So we know that sigma 1,1, which is equal to sigma 3,3 because they're both in that lateral direction, is just going to be equal to epsilon times epsilon, E times epsilon 1,1. If we look up, it says that the Young's modulus is 2 GPa, so we know that this is going to be 2,000 multiplied by the strain, which we have as negative 0.1. So we know that this is going to be equal to negative 200. And this would, of course, be MPa. We can do the same thing for sigma 2,2. So it's going to be equal to E times epsilon 2,2. So it's equal to 2,000 multiplied by negative 0.2. And we get that this is equal to negative 400. So it's a lot of work for this question, as you guys can see. The nice thing for you guys that Dr. Sammer's students didn't have namely me, is that you guys have Mathematica. So of course this is going to go a lot faster for you. If I were to substitute all the values into my strain tensor, I get the following. 0, 0, negative 200, 0, 0, and I'm just going to end the bracket over here. This. So we're not even done the question yet. Isn't that a pain in the ass? We've done all this work so far and we still haven't even answered the question. The question wants the maximum shear stress. So I'll highlight that right here. This maximum shear stress. And we know that for shear stress, I'm just going to scroll up a bit because we don't need that diagram right now. Tau max is going to be equal to 1/2 of the maximum difference between the principal stresses. So while I write this down, I'm going to ask you guys in the chat, does my strain tensor in its current form that we have on the screen, are those the principal stresses? What do you guys think? You guys answer in the chat while I write this down. We'll see what you guys think. We got sigma 2 minus sigma 3, and then we have sigma 1 minus sigma 3. Let's see what you guys say. You guys say yes, you guys are absolutely correct. Because if we look at that strain tensor, we have no shear components. If we have no shear components, then we know that this is actually going to be our principal stresses. So all I have to do is find the difference. So we're going to say 1/2, and then we're the maximum. And let's see what you guys say. What is the maximum, or I guess the absolute value of the difference between sigma 1 and sigma 2? What's the difference between sigma 1 and sigma 2? Keep you guys on your toes. Actually, I like to ask you guys questions so I can take a water break. My throat's been feeling like a desert lately. Just review session after review session. I can't even talk anymore. Yes, thank you, Aaron. It is 200. So that would be the first one. If we look at the second one, the difference between sigma 2 and sigma 3, that's also going to be 200. We know it's technically negative 200, but remember we are taking the absolute value. And then the difference between sigma 1 and sigma 3, well, they're the same value, so it's going to be 0. So we know that our maximum shear stress is going to be 200 divided by 2, which is equal to 100 MPa. If we come and look up at our question here, we see that that is going to be answer number B. So I want to put a little disclaimer here for you guys. It's very rare that one of my questions would be this long. This is a lot of work, I think, for 4%, so I don't think I would have it this long. But these types of questions are definitely fair game on the midterm. So I'm hoping that wasn't too bad. As you're going to see, the midterm has a mix of very short, quick answers and some that do require calculations. But this was a lot of calculations, so I'm hoping if you guys think that this is easy, that's great because everything else is going to be easy. Question number 5. This will not be tested on the midterm because I did not talk about true stress. So I'm putting an X on number 5. It's something that wasn't pre-midterm. It's just I forgot to talk about it, so that's why we're not testing it. As you guys will see, it's a very simple formula. The true stress is equal to the engineering stress multiplied by 1 plus the engineering strain. So if I wanted to answer this question, my engineering stress, it gave us as 300. We have 1 plus my engineering strain, which was 10%, so this would be 0.1. So if we go, it's just going to be 300 times 1.1, which is just going to be that 330 MPa. So it would have been a nice, easy question, but unfortunately, I forgot to talk about it. So it's unfair of me to test you guys on something I didn't talk about. At least that's my opinion. I would never give you guys a question you've never seen before. That's just too mean. I think that defeats the purpose of testing, in my opinion, but of course you guys have seen other professors that fully disagree. So let's move on to question 6. As we can tell, this is also one that's before the midterm, so we will not be testing question 6 at all. Just for fun, who knows what the answer would be for question 6? Who thinks they know what the answer would be for question 6? All right, we got a couple different ones. So C, which is 9, we have 3, and we have 81, all different answers. The correct answer would be 81. And the reason why is we look at these two values. So we have 3 and 3, but here's the key. If we look at this, it's not R. We're dealing with M. So basically, we take that 3 and we have to square it. So we're going to go 3 squared times 3 squared, which is the same as 9 times 9, which is equal to 81. If this was from R3 to R3, then we would remove the squares, basically. Every time you have that M, you have to square whatever value is associated with it. But again, this will not be tested on the midterm. This was something before the midterm. So let's move on to question number 7. Question number 7 is a very good question. It's one of those quick theory questions. It says the limits of Poissons ratio in a linear elastic material are governed by, basically the Poissons ratio has to be greater than -1, but less than 1/2. If the material does not abide by these limits and has a negative Poissons ratio, or a Poissons ratio less than -1, then the following unstable behavior will occur. So this is the key here. What happens when we have a Poissons ratio less than -1? So option A, a positive hydrostatic stress will be accompanied by a negative volumetric strain. Option B, a positive shear stress will be accompanied by a negative strain. Both A and B, or none of the above. So there's no real trick to this question. If you guys were to go to my lecture notes and look at the restrictions on the elastic moduli, the answer would be actually directly there. So again, there's no real tricks. So my question to you guys, what do you guys think it is? Do you think it's going to be A, B, C, or D? What do you guys think? Again, there's no real tricks. This is more or less just definitions. It would come directly from the lecture notes. All right, we got answer B. You guys are exactly correct. It would be answer B. For part A, where we have a positive hydrostatic stress accompanied by a negative volumetric strain, that is a valid unstable behavior, but this occurs when our Poissons ratio is greater than 1/2. So this goes to the other limit on the other side. If we're talking about Poissons ratio that's less than -1, it's always having to do with that shear stress behavior. So if the question was the exact same, but instead of less than -1, it had 1/2 here, or greater than, then the answer, of course, would be A. But that's not the case here. So it's going to be B. We're going to scroll on down to number 8 here. And number 8 actually isn't too bad. It says the shown unit length cube, so unit length basically means that all the dimensions are going to be equal to 1, is in a state of stress represented by the stress matrix below, with the following components. Sigma is equal to 105, 020, and 503. And then it says, then the shear stress on plane BCOG is equal to, and if I were to highlight it, it's going to be this plane kind of at the back end of the cube right here. I'm not very good at drawing shapes. I know I'm just tracing the lines, but it's still pretty bad. So what do you guys think? First question for you guys. Can we determine it directly from the tensor? Can I determine my shear directly from the tensor? What do you guys think? Can I just look at my tensor and know what my shear is on that plane? It's a hard question, right? So that's the key here. If you guys don't know, you guys should always just go to the calculations. When it comes to three-dimensional states, it's very hard to predict shear just by looking at it, because shear, again, it's not really associated with the direction, it's more angles. So never try and guess shear stress. That's going to be kind of my hint to you guys. So if we look here, we say, okay, I know that if I want the shear stress, we have formulas. We have to find the traction vector, and then from traction, we find the normal stress, and then from normal stress, of course, we find the shear stress. And in order to start, we have to find basically the unit vector that defines this plane. So we know that our plane, of course, is kind of pointing outwards like this, plane N. So what would N be as a vector? Do you guys have any ideas what my n vector would be? Any ideas? Yes, exactly. -1 because it's going in the E1 direction, and then the other two components are equal to 0 because it's not going in the E2 or the E3 direction. So thank you for answering. That is the correct answer. And now that we have that, we can start determining everything else. The first step, as I said, is our traction vector Tn, which is going to be equal to sigma multiplied by n. And if you go through the calculations, it's pretty simple. We have -1 plus 0 plus -5. So I think this would be, it's -1 plus 0 plus 0. So this is just going to be equal to -1. Then we have -1 times 0 plus 0 plus 0. So this is going to be 0. And then we have -5 times 0 times 0, or plus 0 plus 0. We have -5. So this is going to be our traction vector. If you guys don't know where this comes from, it doesn't matter. You guys have Mathematica. I like to try and solve it by hand because that's how Dr. Sammer intended it. But again, you guys have Mathematica. I'm not taking that away from you. So if you just become really good at Mathematica, that's perfectly valid. So with our traction vector, we can solve for our normal stress, which is our traction vector dotted with our normal vector. So if we look here, it's going to be -1. Oops, I'll go to highlighter right here for everybody. -1 times -1, so that's going to be just +1, plus 0 times 0 is 0, plus -5 times 0 is 0, so our only component is actually just going to be 1. Nice and simple. Not sure how big my eraser is. I'm just going to get rid of the highlights, not to confuse everybody. Fun little fact. Oh, sigma transpose, it should be. Great pickup. This is the correct form, sigma transpose times n. Luckily for us in this course, and as you guys can see, I fall habit to it, sigma will always be symmetric, so it doesn't matter. But yes, the actual pure formula would be sigma transpose, so thank you for picking up on that. It's a bad habit that I need to get out of. But again, luckily for us, sigma is always going to be symmetric. I promise you guys, all right, here's my Clayton promise guarantee. If I give you guys a non-symmetric sigma, you guys can just answer anything and I'll give you full marks. All right, I'm not going to do that to you. That's too mean. We never covered it, so why should I test it? So if we were to go to, oops, I put n, the shear stress, we know it's going to be the norm of my traction vector subtracted from my normal stress times n. So if you do this, it's basically going to be the norm of the vector 0, 0, -5. You guys can find this through Mathematica. And the norm of that vector, as you will see, is just equal to 5. So if we look at our maximum shear stress, we know it's going to be 5. So it's going to be equal to C. Not too bad at all. At least I'm hoping you guys are thinking, hey, this isn't too bad. If we look at question number 9, just coming down here, it's basically the same question because we have the same state of stress. We are still dealing with a unit length cube, but now it's asking for the normal stress on plane BCFE. So that's going to be this plane right here that kind of runs diagonal through our specimen. So it's going to look something like this. What would change if it wasn't a unit length cube? That's actually something you'll see here. So in this particular case, nothing. But what could potentially change is going to be the normal vector. So if this cube was stretched out long, so let's say that for the question that we just solved, I'll write it in blue here. Let's say that this was equal to 16, like something crazy. Nothing would actually change in this question because our plane is perpendicular to two of the basis vectors. It's very easy to define n. When we look at this question right here though, this is where the dimensions come into play. So I'm just going to highlight the plane really quick. This is our plane, and we know that we need to define basically a normal vector that's perpendicular to this plane. So this is going to be equal to n. It's in this case where things start to change. So what I'm going to do is I'm just going to draw down here for fun, and I'm going to erase this, but just to show you guys what exactly I mean. If I were to look basically down the E1 and E2 plane, just like this, the plane that I just drew is going to actually be something like this, where it goes from 1 to 1. But if the dimensions of my cube started to change, as we can see, the plane, that could also start to change. So this would affect the normal vector. That's a very good question. In this case, it doesn't impact anything because all we're doing is doing the normal vector. So if this was my question for you guys right now, we know that it goes from 1 to 1. Our normal vector is going to be like this, n. What is n going to be equal to? What do you guys think? What is going to be my normal vector in this particular case? All right, drink break's over. No one wants to answer. It's going to be equal to 1 because we're going 1 unit in the E1 direction. Yes, so Aaron got it. It's 1 because we are going 1 unit in the E2 direction, and 0 because we are not going into the E3 direction. But remember, whenever you're dealing with stresses and we go from traction vector to normal stress to shear, n always has to be normalized. So if you were to use 1, 1, 0, you will find that everything actually is wrong. So what we have to do is we say our normal vector n, it's going to be 1 over root 2 and 1 over root 2 and 0. Again, the only thing I did here was I normalized it. That's it. You start off with 1, 1, 0, and then you normalize it. Or since you guys are so big brain, you guys can just go to the 1 over root 2. You guys are smarter than me, so it's probably easier for you guys. Now, after we do that, it's a piece of cake because we can say, okay, if I know what n is, I can find my traction vector, which is going to be sigma transpose multiplied by n. And if we do all the calculations, it's not too bad. It's going to be 1 times 1 over root 2 plus 0 plus 0. So we just have 1 over root 2. If we were to move on to the next component, it's 0 plus 2 divided by root 2 plus 0. So 2 over root 2. And then our final component is going to be, let's just see here, 5 over root 2 plus 0 plus 0. A lot of things are 0, which is great. So we get this as our traction vector. And then all we have to do to find the normal stress, which I call sigma n, is we are just going to take our traction vector and we are going to dot it with our normal vector. That's it. So all we are going to do is say, okay, our first component is 1 over root 2, and we multiply that with 1 over root 2. Well, we know the first one is just going to be 1/2. Then we move to the second component, 2 over root 2 multiplied by 1 over root 2. This basically gives us 2 divided by 2. And then our third component, 5 over root 2 multiplied by 0 is just going to be equal to 0. So as we can see, we get that our normal stress is equal to 1.5 MPa, which is answer B. So hopefully that wasn't too bad. What do you guys think? In the chat, what do you guys think? Is this going to be a pretty easy exam? Is it going to be medium exam? Or is this just going to be a real ball buster? What do you guys think? I'm really curious. I've done it so long now that everything seems easy, but I know that that's that's one of the kind of disadvantages with doing it for so long, is you think it's easy and you lose perspective from a student. Because again, I remember taking this class and it was not easy. It was not really fun at all. So it's good to get that perspective from you guys. So we're going to go to question 10. And question 10 is a nice, simple one. Again, this is a typical question that if you guys don't know this one, this can actually be answered directly from the lecture notes. Specifically, lecture notes 6. It says the position function of a deformed continuum follows the relationship x, where it has those three components, where b is a positive real number. And all it's saying is, what is this type of deformation? So if we were to do this right here, we can see really quick that we have x1 as a function of big X1 and big X2. If we were to look at small x2, it's a function of x1 and x2 as well. So just a quick question for you guys. Do you think we are going to have some shear involved? What do you guys think? Yes or no? Do we have some shear involved in this type of deformation? Anyone betting on shear? No one's betting on anything? Everyone's too tired? That's okay. The answer is yes. If I ever have a position function x1 and it's also a function of a different variable, in this case x2, we are going to have some sort of shear. So right off the bat, if I wanted to, I can eliminate a and b because we know that there is going to be shear involved. If you guys don't know, what you could do is you can actually just say, okay, let's look at my displacement functions. So all I'm doing is I'm subtracting big X1, so I get beta X2, and then in the second column I get beta X1, and then in our last column we get 0. So right away from here, just by finding these displacement functions, we know that it's not rigid body rotation or translation. If it was rigid body rotation or translation, my displacement function should be 0 because it shouldn't really be displacing, or it should be a constant value. It shouldn't be a function of x2 or x1. So now basically we are left with two different ones. One is simple shear. So this is when my shape kind of turns into something like this. So two of the sides don't really deform. It's just that one side. It looks something like this. And then we have pure shear, where pure shear is when both of the sides kind of deform. I can never draw it very well. So now if we were to look at our displacement function, oops, that's the eraser, and that's not the highlighter, is one side a function of the other side? Basically, is this first component dealing with x1 a function of x2? Does that first component contain an x2? Yes. That means that there's going to be shear on one side. If I look at my second component, our second component is now a function of x1, but it should be a function of x2. So this indicates that there is shear on both sides. So this is actually going to turn into pure shear. All right, pure shear. Hopefully that makes sense. But again, it's one of those questions that if you don't know and you were to go to my lecture notes for this specific topic, it actually shows you what exactly pure shear is, and you will find that my displacement function for pure shear is equal to this. If it was simple shear, one of these would be 0. That would be simple shear, where it's only one side that is shearing. Since we have both sides shearing, that's how we know it's actually going to be pure shear. Again, it's one of those ones you kind of just look at. So it's pure shear because there's x1 and x2. Yes, it's basically my displacement function, u1, is a function of x2, and my displacement function u2 is a function of x1. So that's kind of the trick there. If we didn't have any shearing and we were just expand it, u2 should only be a function of x2. That would be just simple expansion or contraction. But since this direction is now associated with the perpendicular direction, that's how we know that we actually have some shearing going on. So yeah, it's a great question. All right. So let's move on to the next question. Question number 11. Now, I'm not going to lie, this is definitely the longest question. I'm not too sure what Dr. Sammer was hoping would be attempted, because there's basically the long way and then there's the short way. Well, actually not 11. 12 is the long one. 12 is the long one. So as I was saying, or just take what I was saying, put it on hold. Let's answer question 11 first. It says the position function of a continuum has the following relationship, and it gives us the three position functions. It says if the material is linear elastic isotropic with a Young's modulus E and a Poissons ratio, then the value of sigma 1,2 associated with the deformation is equal to, and basically all we're doing is solving for sigma 1,2. But we know that if we want to find a value of stress, we need to have its corresponding value of strain. So this question is also a lot of work because first we have to find our actual strains involved. So if we were to look at this one, we say, okay, we have position functions. From position functions, we can find displacement functions. So I'm going to say, okay, my displacement function u is going to be basically my position functions with big x1, x2, and x3 subtracted from them. So for small x1, we have x1 plus 0.12 x2. So once I subtract big x1, we just get 0.12 x2. If we look at small x2 and we were to subtract big x2 from it, it's just going to be equal to 0. And then the same thing for that third component. So if we were to look at this really quick, and let me ask you a question, would this be simple shear or would this be pure shear? What do you guys think? Would this one be simple or pure? Simple, exactly, because we only have x2 on one of the components. We have the other component equal to 0. Perfect. So now that we have this, we can then find our displacement gradient, nabla u, by taking the partial derivatives. So it's pretty simple. So if I were to look at that first function, 0.12 x2, and take the derivative with respect to x1, well, it's going to be equal to 0 because there's no x1. If I were to take the derivative of that with respect to x2, well, there is an x2 in this case, so we get 0.12. And then if I were to take the derivative with respect to x3, it's going to be equal to 0. And if we were to look at the displacement functions u2 and u3, they're both equal to 0. So it doesn't matter what I take the derivative with respect to, it's always just going to be just a bunch of zeros. So it's going to be like this. Now from here, we can find our strain tensor, epsilon, by simply going 1/2 of nabla u plus nabla u transpose. So what's nice here is the only components that we have to worry about are going to be those two shear strains. If we were to look at our normal strains, they're all going to be 0. So I'm going to have a 0 there. The next one, this component right here, if we were to look at our formula, and I'm going to do it down here really quick and then erase it. So we say epsilon 1,2, it's equal to 1/2 of nabla u12, which is going to be 0.12. So 0.12 plus the transpose of nabla u12, which is going to be this value down here. So we're going to have plus 0, and this is going to be equal to 0.06. So I'm just going to erase this up here. I have to write a little bit small because there's not a lot of room to work with. 0.06, 0. You'll find that down here it's also 0.06, 0, 0, 0, 0, and 0. I'm just going to make this 0 look a little bit nicer. It looks pretty gross over here, so I'm just going to fix that up like that. And if you guys are wondering where this value came from, right here, it's basically this formula, but we go 1/2 of 0 plus the 0.12. That's what would happen basically with the transpose. So I'm just going to erase the highlighting really quick because we now have our shear strains, or our shear strain, singular. There's just one of them, I guess. Now what's nice is if we are converting between shear stress and shear strain, remember they are decoupled. Shear stresses and strains are not related to the longitudinal or the normal stresses or strains, which makes it nice because calculating them is very simple. If you guys were to go to our relationships that we had, it turns out that 2, and this comes right from our relationship, 2 times epsilon 1,2 is simply going to be equal to sigma 1,2 over g, where g is our shear modulus. So if we were to look at this equation, We know what epsilon 1, 2 is now, and I'll highlight it over here because we just solved for it in our strain tensor. We know what 2 is. The only thing left that we don't know is actually going to be G. But G is nice because there's a set formula for it. G, which is our shear modulus, is going to be 1 plus 2 nu, and then this is the denominator, and the top we have E. What's nice here is we have all the parameters we need to solve for this. So on the bottom it's going to be 2, 1 plus 0.2, or was it 0.2? Yes. We are given that Poissons ratio is 0.2, E is 2000 MPa, so all I have to do is substitute everything accordingly, 2000, and we get our shear modulus is around 833. 833. So now if I were to look at this equation, I can rearrange it to solve for sigma 1, 2. Sigma 1, 2 is going to be equal to 2 multiplied by our shear strain, 0.06, multiplied by G, which we had as 833. And if you guys were to just throw that into your calculator, it's actually kind of funny because it turns out to be exactly 100. So 100 MPa. So our answer for this question is going to be C. Isn't that great? A lot of work, but it's not hard work. It's just a lot of steps. The thing that made this question so bad is that we had to find the strain tensor first. If the question just gave us the strain tensor, well, then we just jump to all the work we did on the left-hand side, which is some pretty simple calculations. So hopefully it's not been too bad thus far. We are going to scroll down to question 12. Now, question 12, this is going to be probably the longest type of question. This is the one I was telling you guys about where I wasn't quite sure if Dr. Sammer expected you to just kind of know this, because it's more or less an identity rather than an actual problem that you solve, or I wasn't sure if he expected everyone to actually calculate this. So what we are going to do is we are going to calculate it, because why not? We'll show you guys exactly where it came from. But as you guys are going to see, this is an identity that we can actually use later on once we start talking about strain energy. All right, strain energy. This will come up a couple times. So it says if a linear elastic isotropic material with a bunch of parameters E, nu, and as well as K is pulled in with 3 positive tensile normal stresses, sigma 1, 1, 2, 2, and 3, 3, then the associated volumetric strain is... So basically all we're doing is solving for volumetric strain. Volumetric strain, in essence, is actually very simple. If I wanted my volumetric strain, it's just going to be the trace or the sum of my normal strains. So it's going to be epsilon 1, 1 plus 2, 2 plus 3, 3. So if we were to look at this, that actually isn't too crazy. The problem is since all of our normal stresses are different, our equations to find each one of these strain values can get pretty long and pretty complex. So I'm going to go to the other side and say, okay, epsilon 1, 1 for a linear elastic material is going to be sigma 1, 1 over E minus the Poissons ratio times sigma 2, 2 over E minus the Poissons ratio sigma 3, 3 over E. And that's just for epsilon 1, 1. So we say, okay, well, what about epsilon 2, 2? Epsilon 2, 2 is going to be equal to negative nu times sigma 1, 1 over E plus sigma 2, 2 over E minus nu times sigma 3, 3 over E. And then, of course, finally, our last one is going to be epsilon 3, 3, which is going to be equal to negative nu sigma 1, 1 divided by E minus nu times sigma 2, 2 divided by E, and then plus sigma 3, 3 divided by E. See, looking pretty gross already. Because before, to simplify these questions, is usually we say that sigma 2,2 and 3,3 are 0, or we say that all of the stresses are equal to each other. But in this particular case, nothing really cancels or goes away. So all we're basically doing is taking our formula over on the left-hand side here for our volumetric strain. And as we can see, when we add everything together, we basically have 9 components. 9 components. But it simplifies quite nicely. So what you guys will find is this. And what's nice for you guys is you can just throw it into Mathematica and simplify it in there, which is always really nice. So what you'll see is that we'll have sigma 1,1 multiplied by 1 minus 2 nu divided by E plus sigma 2,2 multiplied by 1 minus 2 nu over E. So there's 2 components, plus sigma 3,3 multiplied by 1 minus 2 nu over E. So we're still kind of in the thick of things, because if we compare what we have now to the answers given, well, our expression is a lot longer. So kind of the next hint that we have, if we were to look in these expressions, they talk about using K. So in expression expression A and B, as well as in the question, it talks about K. And K is our bulk modulus. So what you guys will find is that if you look at the formula for K, which we have in our slides, it's equal to E divided by 3 multiplied by 1 minus 2 times nu. And this is where things start to get a little bit fun, because if I look at this, I have 1 minus 2 times nu and E on the other side. And if I look at all these components, I have that in each one of these components. So I'm just going to erase all the highlighting really quick, because you guys now see what I'm talking about. The only thing that I actually have to do to try and make this more applicable is I have to move, and I'll do this in pink, I have to move this 3 to the other side. So if I were to multiply both sides by 3, we have 3 now at the top. We get rid of the 3 at the bottom. Therefore, we can replace each one of these parameters. Oops. Yeah, let's do it in pink. I can now replace each one of these parameters in my equation now with 3K, which is great. So as we'll see, this expression actually turns into sigma 1,1 plus sigma 2,2 plus sigma 3,3 all divided by 3K. The key thing to keep in mind is that we had to move that 3 to the other side, which is why we have 3 on the denominator. If we were to compare this to the actual question, it's going to be answer A. Notice that answer B almost looks identical, but it doesn't have that 3 there at the bottom. And that's what it'll try and trick a lot of students with. Options C and D, well, they're just too crazy. They don't even have K. So we know right off the bat that those ones are unlikely to be the answer. This was probably the longest question. Again, it's more of a kind of an identity that we'll use a lot later on, so you guys will learn to know this. But yeah, it's kind of a long question for 4% of your marks. So I'm not a big fan of long questions. If they're only worth 4% of your mark, that's a bit mean. So we'll move on to question number 3. Does anybody have any questions so far, or are you guys doing good? You guys sleeping yet? I don't know why. I had to wake up at 4:30 in the morning to use the washroom, and then I just couldn't go back to sleep. Don't you hate it when that happens? When it's like an hour before you actually have to get up, and then you just lie in bed awake because your mind starts going? Oh, it's the absolute worst. Oh, yeah, no, I got a direct message. Sorry, just going back to question 11. Will all the material be isotropic? So in question 11, it says directly that, material, yes. It says it's isotropic. But to answer your question in a more general manner, it will not always be isotropic. I could give you in your exam a transversely isotropic material, or I can also give you an orthotropic material. Now, the thing to keep in mind with those those types of materials is the equations become a lot more complex. There's a lot more variables involved. So if I were to give you an orthotropic material, chances are it'd be having to do with shear, because then there's not a lot of parameters involved or something like that. I'd give you a simplified version. Maybe I say that a lot of the stresses are equal to 0 to cancel out a lot of terms. So in general, no, I can test you on orthotropic or transversely isotropic, but I would never give you a question this long for those types of materials, because that's just cruel. So hopefully I answered your question. I'm not too sure if I did. It's a very good question that I'm sure a lot of people were wondering. All right, so we are going to move on to question number 13, where it says the stress at a point is given by the following matrix, where A is a real number. So if we look at that matrix, our stress matrix, A is the only component, and it's sigma 1, 1, and there's A involved with sigma 2, 2, the rest is 0. It says if S is the deviatoric stress and P is the hydrostatic stress, then basically which of the following is true? So let's just go through them one by one. Is A true? What do you guys think? You guys in chat. Is A true? Who thinks A is going to be true? Then my deviatoric stress is going to be my stress subtracted from P times I. Any takers? Yes? Exactly, yes. If you guys were to go to the lecture notes where we talk about deviatoric stress, this is the actual definition right here. Definition. If I were to calculate definition, I forgot how to spell it. This is how we would actually calculate it. So this is definitely going to be true. Now, always be careful with these types of questions, because if I know this is true and I circle A and move on, well, you can kind of screw yourself, because if we look down here, we have an all of the above option. So we actually have to check the other two. So if we're looking at this and I actually want to calculate my deviatoric stress, I need to figure out what my hydrostatic stress is. So we know that P, our hydrostatic stress, it's just going to be the trace of our stress tensor. So these three components, these three diagonal components added together and then divided by 3. So we have A plus negative A plus 0 all divided by 3. And we end up seeing that our hydrostatic stress, P, is actually just going to be equal to 0, because A subtract A is going to be 0. So if this is the case here, then this means that S is equal to sigma minus 0 times I, which is just equal to sigma. So if we look at option B, it's basically saying that S is equal to sigma, so we know that B is also correct. So again, we prove that A is correct. We now know that B is correct. And then if we look at option C, where it says the hydrostatic stress is 0, well, we already calculated that to be 0, so we know that all three of these are actually correct. So therefore, our answer is going to be option D. Hopefully that wasn't too bad. The main goal of this question, don't rush through the exam. Just take your time, have fun with it. That's what 398 is about. Are you guys having fun so far in this course? Are you guys having fun? Do you guys say, wow, I wish I had more 398 in my life? I'm hoping so. Probably not. Oh, thank you, Aaron. You're flattering me. But I know that you guys don't really care about this course, and it's a hard course to like because we are dealing with stuff that's already been programmed. Again, this is basically how we simulate things. But if we go to most computer programs, well, it's already calculated how we simulate things. It's definitely good to know what's going on, so that's the purpose of this course. But I know that you guys want to go into the real world and have some fun, so I appreciate you guys flattering me, of course, but I know the truth. And the reason why I know the truth is because I was in your shoes once. This course meant absolutely nothing to me, if I'm being completely honest. But I'm glad it means something to you. All right, let's move on to question number 14. It says the shown figure represents a specimen under confined compression test on the onset of failure. On the onset of failure. Basically, what this means is that under these applied loads that it currently has, it's about to yield, or it's basically yielding. Remember in friction where we had impending motion, where we said at this point it's not moving, but it's on the verge of moving? Well, that's what we have here. It's on the onset of failure. So we can say that the stresses that it's currently subjected to, this is going to make it fail. So if we were to look at these stresses and put them into tensor form, so I'm just going to draw a quick little tensor. We see that 1, or sigma 1, is negative 100. We have no shear. Sigma 2 is negative 400. We have, again, no shear. And then sigma 3 is negative 100. And we have no shear. So I just like to draw the stress tensor. It helps make the calculations a little bit not easier, because at the end of the day, the calculations, of course, are going to be the exact same. It just helps me visualize what I need for my formulas a little bit easier. So I'll just move this kind of over to the side. All right, so it says, if the material follows the von Mises yield criterion, or in other words, the failure occurs when the applied stress is equal, or the yield stress is equal to the von Mises stress, then for this material, what is sigma max? So it's kind of worded a little funny, but in essence, all this question is asking for is, what is going to be our von Mises stress? Because our von Mises stress, it says, is equal to sigma max. So all I need to do is figure out what that von Mises stress is, and we know that we have a formula for it. So I'm just going to scroll up, and we can say, oh, I got a question. Would changing the basis change the stress vector? For example, having negative 400 as sigma 3. Yes, it would. So if I were to pick different coordinates, then yes, it would definitely change what's going on in my stress tensor. But what you will see is that even though our stress tensors are different, so let's say that this is what I normally do, right? So I'm just going to draw what I normally do. I have this. In this case, I have the stress tensor on the left. But let's just say for fun, I don't know, maybe I get a little inebriated or something like that, and I end up with the following basis. Again, don't ask me how. You never know. Sometimes you get a little crazy. We will have a different stress tensor, and we will have shear in that stress tensor. The nice thing, though, is even though the components are different, they will give us the exact same von Mises stress. So it doesn't really matter. The only thing is if we were to look at this tensor, that is very hard to calculate the components. So it's better to just align everything with the applied loads, or else things start getting a little bit crazy, if that makes sense to you. I'm hoping I'm answering your questions. It's definitely a very good question. And even if this were Tresca instead of von Mises, it doesn't matter, because remember, for Tresca, we need everything in terms of these principal stresses. So even if it was Tresca, we would need our tensor in this very specific format. So all we need to do in this question is figure out the von Mises stress, and that's easy for you guys. Remember, in the lab, I told you, or I guess not the lab, the seminar, I said, everybody, make a very nice code for your von Mises stress so that you can substitute basically any tensor into it and get that von Mises stress. So all you guys would have to do now that you know the tensor is throw it into your Mathematica code. You'll be good to go. I don't have Mathematica, so I kind of do this the long way, but it's not too bad of a formula. It's going to be negative 100 minus negative 400, and then this will be squared, plus, it makes it easier since we have no shear components at least. Negative 400 minus negative 100 squared, plus negative 100 minus negative 100. I know that some of these cancel out, but I like to be thorough for you guys. I'm going to have to move this a bit. Of course, it's getting a little bit too long. So we'll just pop it on over here. This is the last component, actually, so I'm just going to close my bracket here. I'll extend this. I drew that a little high. All right, let's make it a little bit nicer. We got nothing but time. I know you guys roll your eyes every time I say that we got nothing but time, because you guys are swamped with everything else, but I got nothing but time, so I might as well make it pretty for you guys. You guys deserve everything nice and pretty. So all we would have to do is just throw this into your calculator or throw it into Mathematica. And what you will get is this is actually equal to 300 MPa, which is going to be answer C. Now here's kind of a fun little trick when we go to question 15. It says the shown figure represents a specimen under test, blah, 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 blah. And if we look at the two stresses from question 14 to 15, they are exactly the same, right? They are exactly the same. And basically the question is saying if this material follows a Tresca yield criterion, where the material fails when the maximum shear stress reaches tau max, what is tau max? So here's the fun thing. If we know that sigma y, basically our yield stress, is 300, how can I find tau max? Is there a relationship between tau max and sigma y? You guys remember? What is the relationship between tau max and sigma y? Anyone feeling brave? Come on, Aaron, I believe in you. You answered all my questions. Jared, anybody? It's okay. I know it's tired. It's 7 o'clock. No one's got time for that. Thank you, Jennifer. Coming in clutch. Tau max is equal to sigma y divided by 2. And if we know from the previous question that sigma y is 300, it's going to be 300 divided by 2, which is equal to 150, and I'll put MPa. MPa, so we know it's going to be equal to answer A. But again, let's just say that you guys didn't know that. Oh, question. How do we know when to use the Cauchy stress tensor properties or von Mises or Tresca? Great question. I will specifically say, so if I want something to do with von Mises, I have to specify von Mises. If I want Tresca, I have to specify Tresca. If I don't specify, then you guys can say, hey, Clayton, you didn't specify, give me the mark, and I'll have to give you the mark. I have to specify which criterion I want from you guys. So hopefully that makes sense and puts you at ease a little bit. Could this have been done with Cauchy, though, for question number 15? 14, no. So that's just it. Is basically when we start talking about maximum stresses, it's very hard to quantify a three-dimensional stress state with one single number. That's the trick here. Is we are quantifying basically a three-dimensional stress state with one single number. In that case, we have to use something like von Mises or Tresca or something like that. There are different criterions, of course. It's not just von Mises and Tresca. There's a bunch of different ones depending on the scenario. That's a great question. We're going to come back down to question 15. And again, we have our little trick, but let's just say we forget the trick. Let's just say that we forgot it's sigma y divided by 2. Well, it's not too bad because we remember that tau max is equal to 1/2 of the maximum difference between the principal stresses. And if we look up, we have our stress tensor. So if we were to say, okay, the difference between -100 and -400, well, that's going to be -300, but the absolute value is going to be 300. If I were to look up again, we have -400, -100, we have 300, and then the last one's going to be 0. So we know that this is going to be equal to 1/2 of 300, just like above, which gives us 150 MPa. So again, if you guys don't know the trick, it's okay. You guys can figure it out pretty quickly. All right. So this question's a fun question. It's one of those questions that has to do a lot with words. Oh, sorry. How do we know the value for sigma y? It's one of those things that from question 14, if we are saying that the specimen is failing and we calculate the von Mises stress under that load, we assume that failure in the von Mises criterion is equal to yielding. This right here, sigma max, this is just another way of saying sigma y. We don't like to use yielding all the time because what happens is a lot of people associate it with steel, even though other materials may yield. So they're kind of interchangeable. Yeah, no problem at all. Perfect. So question 16, it says the longitudinal engineering strain on the surface of a test specimen were measured using a strain rosette to be 0.04, 0.04, and negative 0.04 in the three directions A, B, and C, where A is 1, 0, B is 1, 1, and C is 0, 1. If the material is assumed to be in a small strain state, then the strain component epsilon 22 is equal to. So basically we're trying to find epsilon 22. Now, what basis vector is epsilon 22 associated with? Who remembers? What basis vector is epsilon 22 associated with? E what? Exactly. Thank you, Aaron. This is associated with E2. What is the vector for E2? How do I define E2? If I were to just keep it in 2 dimensions, what would my vector be for E2? Thank you, Aaron, again. It's going to be 0, 1. So all I need to do is find the strain in that particular direction. And it's nice because if we were to look here and we were to look at direction C, it's 0, 1. It's in that basis vector. So we know that it is going to be the strain associated with direction C, which is that negative 0.04. So our answer in this case is going to be equal to D. All right, so hopefully that wasn't too bad. Again, just look at the direction for that one. Question 17, this is the one where I'm going to make a note. I talked about it in the last seminar, or I guess review session. I'll do it again here. I will not test you guys on pipes. I promise you guys. I will not test you on pipes. So this is something that we are not going to cover. I have the solution. As you guys know, the solution to this is actually very, very simple, but I will not be testing you guys on pipes. So this will not be in the exam. We're going to move on directly to the next one. So question number 18. We're going through this actually at a pretty good pace. An object expanded such that the original position x, then the final position vector is x, or small x, which is 1.1x. The small strain matrix associated with this deformation is equal to, and let me just ask you a quick question, because I know some of you guys were here yesterday. Was this question in the exam yesterday? Did we cover this almost identical question? Who remembers? Yeah. But was it the exact same question? Was this the exact same question as yesterday? I know it's hard to tell. The answer is no. So this is where it gets tricky, and the point I'm trying to make with this is we have to read very carefully. Yesterday, all the numbers were the exact same, all of the answers were the same, but yesterday it wanted the green strain matrix. Today, we just want the small strain matrix. So it's actually easier than yesterday because the green strain matrix takes a little bit more effort to find. So if we were to look at this, we say, okay, we know our position function is just going to be 1.1 times x. So we have 1.1 in the x1 direction, 1.1 x2, and 1.1 x3. So it's not too bad at all, because if I were to subtract x1, x2, and x3 to find our displacement functions u, well, we are basically just taking 1.1 and subtracting 1. So we're left with 0.1 x1, 0.1 x2, and 0.1 x3. Kind of. I know my brackets are actually getting a little bit crooked. Sorry about that, guys. I apologize. From here, we can find our displacement gradient, nabla u. I'm hoping that since we've done so many examples, it's kind of burned into your brain by now that we always go position, displacement, displacement gradient, small strain tensor. It's kind of always that exact same process. This is really nice because our displacement gradient is just the partial derivatives of all those functions, which are very simple. So it's going to be 0.1, 0, 0, 0, 0.1, 0, 0, 0, and 0.1. And if you were to find the small strain tensor, E small, we know that it's actually just going to be equal to 1/2 of nabla U plus nabla U transpose. And since we don't have any diagonal or non-diagonal components, or basically since we don't have any shear, we know that our actual strain tensor in this particular case, for the small strain tensor, it's actually just going to be equal to our displacement gradient. Isn't that nice? So we know that this is actually going to be E small. So if we were to compare this to the answers that are provided, we can see that this is going to be option B. Last night when we did the green strain tensor, it was actually option D. So they are going to be different. So it's one of those things that please make sure you read the question very carefully. It's one word, and these questions are two completely different questions. The only difference between today and yesterday was instead of small, oops, I wanted to just do this, all it did was say green. That was it, and it changed everything. So please be careful when you're reading these. That's probably the worst trick that can happen. All right, let's go into the fun. It says the stress matrix as a function of the position in a continuum is given by the following expression, where alpha and beta are real numbers and they're basically constants. Then the equilibrium body forces vector applied to this continuum is equal to, so if we look at this, it's very clearly one of those momentum balance equilibrium equations question. So all we need to do to find our equilibrium equations is we take the partial derivative of the columns of our stress tensor, we add it to our body forces, and then we set it equal to the acceleration vector. Now, one thing that I noticed that Dr. Sammer didn't do was he didn't mention that we are actually considering a static equilibrium. So we know that our acceleration is going to be equal to 0. So let's just start with equation 1. So equation 1 focuses on that first column, and I'll erase these two. It just focuses on the first column. So negative 3x1 with the derivative with respect to x1, well, we're going to have negative 3. Then we say, okay, that's going to be added to the derivative of x2 with respect to x2. So this is going to be plus 1. And then the derivative of 2x2 with respect to x3, that's going to be equal to 0. Now we add this right here to our body forces, and we set this equal to our our acceleration vector. But since we are dealing with a static case, this is going to be equal to 0. So right off the bat, one equation, one unknown, we can figure out that rho b1 is equal to 2. So again, it's one of those things that even though the only answer that has 2 is going to be C, we can never rush these things because of this none of the above. What happens if rho b2 and rho b3 are not equal to negative 1? It would create a lot of problems. That'd be a very mean trick. So far we know for a fact that it's not A and it's not B. The question is are the last two components negative 1 and negative 1? So, oops, I forgot to say equation 1. We're going to go to equation 2. And now we are focusing on the second column. So we have alpha x2 with the derivative with respect to x1. Well, that's just going to be 0. Our second one, we have the derivative of x2 with respect to x2. That's going to be equal to 1. And then we have a 0, so it's going to be 0. Plus rho b2 is equal to 0. Therefore, rho b2 is equal to negative 1. So far, so good. But remember, we have to check all of them just to make sure. We go to equilibrium equation number 3. And we are focusing just on the last column. So it's going to be this one right here. The derivative of beta x2 with respect to x1, that's going to be 0. The derivative of 0 with anything is going to be 0. And then the derivative of x3 with respect to x3 is going to be 1. Plus rho b3 is equal to 0. We know that rho b3 is equal to negative 1. So it does check out, and in this case our answer is indeed C. So hopefully that wasn't too crazy for you all. I know sometimes they get a little crazy, sometimes they don't. I just wanted to see what you guys are thinking. All right, question 20. Question 20 is a mean question. I'm not going to lie to you guys. Question 20 is a mean question. Whenever you guys have the change in angle between two vectors, it's usually a pretty mean question. But for you guys, it's not. And the reason why is this. You guys have Mathematica. The reason why this question is mean is because the formula for this is actually pretty gross, in the sense that it's not easy to do by hand. Of course, it's doable, but it's not the easiest. So what we're going to do is we are going to look at it. It says the position function of the shown unit length cube after deformation follows the relationship, and it gives us the position function. And it says, using the small strain matrix, the angle between the vectors OG and OE after deformation is equal to. So if we were to look, we have vector OG, which comes here, and then we got vector OE, which goes like this. Now, one of the things that we will need is our angles before deformation. So currently, let's ask you guys in chat, what is the initial angle between these two vectors? 90, exactly. We know that they are going to start off at 90 degrees. The next thing that we need for our formula, as we remember, is going to be the two vectors themselves. So what I'm going to do is I'm going to set dx equal to the vector OE, so it's going to be 1, 0, 0. And I'm going to set the second vector dy as OG, which is 0, 0, 1. So far so good. The problem becomes when we actually take a look at the formula. So if you go to the lecture slides, we have a nice formula for figuring out the change in angle between two vectors. It was cosine of the final angle minus cosine of our initial angle divided by 2. And this is going to be equal to dx, which we now know, dotted with e dy, which we know. The only thing we don't really know right now is strain, multiplied by the norm of dx divided by the norm of dy. So if we were to look at this equation, we could technically solve for theta f. This is going to be our only unknown. The only thing that we need to do first is we need to figure out what our strain tensor is. So again, this question, it's not a bad question. It's just a lot of work. You have to go through all of those steps. So we know if we want strain, we basically have to find our displacement function. So I'm going to come over here. Oops. I'm going to say u, our displacement functions, and they're just going to be x minus big X. So we're going to have 0.02, x2, 0, and 0. From here, I can find the displacement gradient, and then I can find my strain tensor. So I will just give you guys the strain tensor, because again, you guys are going to be doing this in Mathematica. You get the strain tensor as 0, 0.01, 0, 0.01, 0, 0, 0, 0, 0. Now, at this point, we know everything on the right-hand side. We have dx from above, we have dy from above, and now we figure out the strain tensor. So I'm not going to show you the calculations. They're actually not too bad, but again, you just throw it into Mathematica. And what we find is that this right-hand side is equal to 0. Now, if our initial angle, theta I, oops, let me go to blue, theta I is equal to 0, what is this term right here? Cosine of theta I, or sorry, not equal to 0, 90 degrees. Cosine of theta I, if I is 90 degrees, or theta is 90 degrees, what's that going to be equal to? 0, exactly. So this automatically goes away. So we're left with cosine of theta f divided by 2 is equal to 0. So what is going to be theta f? What is going to be my final angle? 90? It's equal to 0. I fooled you guys. It's definitely going to be 90 degrees. As soon as I saw the question mark, Aaron, I thought I would take advantage. I'm sorry. But yes, because we know that cosine of theta, if it's equal to 0, oops, I just about put 90. If it's equal to 0, we know that theta is going to be 90. So it's going to be this. So these two actually don't change. And the reason why is this. If I were to look at my diagram, and I'm going to zoom in, under the type of shear that we have, we are shearing in basically the E1, E2 plane. So what actually happens to this, I don't know what to call it, cube, even though it's not really a cube, is it actually looks like this, where it shears kind of like this. So this comes out. I know it's not something that's very easy to picture, but this is actually what's happening. So if that's the case, do the bottom and top surfaces actually shear? Well, not really. But it's one of those things that it's very hard to just visualize it based on the equations. So if you have a question like this in the final, not the final, sorry, the midterm, I recommend just going to the equations. You guys have Mathematica. You guys can even start doing the equations tonight or tomorrow, like pre-writing them, and then just go for it. So it's not too bad at all. We're going to move on to question 21. Again, we have our unit length cube. This time it was very generous in that they gave us the strain tensor. And it basically said, what is the small strain along line OG? So if I look at OG, it's this line right here. Oops, I don't know why it made it look bad. It's this line right here, OG. Now, is this line in the direction of a basis vector? Oh, sorry, in the formula where is it dx times e dy? What e do you use? This is it right here. This would be the strain tensor. So this right here, these two components together, it's a matrix times a vector. Yeah, it gets really gross. That'll give you a vector. Yeah, good question. So we're going to go back to this one. Is line OG along one of the basis vectors? Yes, it's in the E3 direction. So we know that the strain along OG is actually just going to be epsilon 3,3. Nice and simple. All I have to do is go to my strain tensor now, find out which one is epsilon 3,3, and that's going to be my answer. It's going to be equal to 0.03. Nice and easy. Not too bad at all. Now, question 22. This is a question that is kind of pre-midterm. Again, I'm not testing pre-midterm, so this will not be on the midterm. All this is a dot product proof, basically. This would be for midterm 1, not really midterm number 2. So we are going to get rid of that. And we are going to go to question 23. Now, question 23 gives a really good... I got a direct message so you guys can't see it. Will the final be cumulative? Yes, it will. The final will test everything. And that's one of the reasons why when I upload the PDFs of these solutions, I will have the answers for all the questions. I'm not just going to do midterm 2. I will have everything so that later on you guys can use this to study for the final, which should be good. Hopefully that answers your question. All right, question 23 here. This is a fun question, and this goes to kind of the special case where what happens if the line we want the strain about is not along the basis vector. So remember, before we found OG, which was along a basis vector, but now we want it along OA. So if we look, O is at the origin, A is at the top corner, so our line is going to look something like that. Is this along a basis vector? Well, definitely not. So in order to, I got a question. So mathematics is a necessity for a midterm, or can everything be calculated by hand? I would say that you can do it by hand. I don't think it was too crazy. The reason why is because if I had to use Mathematica to create the questions, which I never did once, I'm assuming that if I could create the questions without Mathematica, you shouldn't need Mathematica. It's one of those ones that just makes your lives a lot easier, so I highly recommend it. It's something we are going to be using a lot, especially in the later labs. I'm not sure who went to the seminar today. I'm hoping it was a good seminar. But yeah, Mathematica is something we use a lot, so it's nice to know it. But there wasn't a time when I created the midterm where I needed to use Mathematica at all. So it should be fine without it, but that's being bold. If you can use Mathematica, why not? Sort of thing. So yeah, it's up to you though. You guys are much smarter than me. I know I could never do this math in my head when I was your age. Oh, I feel like an old man now. All right, we're going to go back to the question. So now we're finding the strain along a line that is not aligned with any of the basis vectors. So this is actually not too bad at all, because all we need to do to find the strain along an arbitrary line is just define what that line is in terms of a vector. So if I'm going dx, we know that this vector is going to be 1, 1, 0. I'm going from point O to point A. So 1 unit in E3, 1 unit in E2, and 0 units in E3. The nice thing about the formula we're about to use is that this vector dx, and even going back to the previous couple of questions, dx and dy, they don't need to be normalized. All right, that's very nice for us. They don't need to be normalized. And the formula I'm talking about is this. The strain along vector dx is going to be equal to dx dotted with epsilon dx divided by, oops, that's not what I wanted, sorry, got a little crooked there, divided by the norm of dx squared. So I have what dx is, I have what my strain is, I can throw it all into an equation. So the vector dx we said is just 1, 1, 0, and we are dotting this with e times dx, which if you guys do the math is 0.03, 0.04, and 0.041. So not too bad. And then we divide it by the norm of dx squared. The norm of dx, if you do it, is root 2, and we were to square it. And if you guys basically just throw everything in, you will get that the strain is equal to 0.035. So that's going to be answer B, just like that. Question 24, nice and simple. It says creep is a material property defined as the increase in stress under constant deformation, the increase in strain under constant load, the general response of a viscoelastic material, or all of the above. So what do you guys think? Is it going to be A, B, C, or D? What is creep? Any takers? It's going to be B. Exactly. Thank you, Jared. Creep is basically if I were to have a sustained load on a beam, it's going to start deflecting. So if it's going to start deflecting, we know that its strain is increasing. Option A, the increase in stress, that is, it's actually increase in stress. That actually doesn't happen. This right here is the opposite of stress relaxation, so that actually doesn't happen ever. C, the general response of a viscoelastic material. Again, that's also incorrect. Only some materials experience creep. If you guys take design courses, you'll never really see steel deal with creep too much. It's usually just concrete and timber. And all of the above is clearly wrong. Question 25. This is one of those questions that is pre-midterm, so we are not doing 25. And this will give us to our last question, and our last question is a nice simple question. Let x equal qx, define a rigid body rotation. So Q is just a rotation matrix. Then the associated green strain matrix is basically which one? So tell me this, first of all, if I were to take an object and I were to simply rotate it, will there be strain? What do you guys think? Will there be strain? No, exactly. So what should my strain tensor be, theoretically? It should be all zeros. Which strain tensor would be all zeros? Would it be the green strain or the small strain? Is the green strain all zeros or the small strain all zeros? Small strain isn't all zeros. The green strain is. So of course it's going to be A. These options down here, it's actually this, you'll never get this one, but this one right here, this is our small strain tensor. And remember, small strain tensor we say is valid for small deformations. If theta is equal to something like 0.001, well then cosine of theta is approximately equal to 1, and then we would get 0 for all of those components. It's one of the limitations of the small strain tensor. It saves us computation time and stuff like that, but if the displacement is large, it will start predicting strains under rigid body rotation. So if I want kind of the full theoretical tensor that will predict 0 strains no matter how large a deformation is, it's going to be the green strain tensor. And that is it for the 2015 midterm. So I hope you guys didn't find it too bad. I didn't find it too bad. So you will have this to study from. You guys also have 2014, which we did last night. 2016, you guys can do that on your own time. And if you guys do all three, I think you guys will be just fine for the exam. There's no real tricks in this. Sorry, can I explain where I got the 300 in question 5? Yes, of course I can. So question 15. So right here, the 300, what this is, this formula, I'll write it over to the side, is tau, oops, gotta go back to pencil. Tau max is equal to 1/2 of the maximum difference between the principal stresses. So it's going to be sigma 1 minus sigma 2, or sigma 2 minus sigma 3, or sigma 1 minus sigma 3. So 3 different options. And where do I find sigma 1, sigma 2, sigma 3? Well, they are coming directly from in here. I have all 3. Perfect. All right, awesome. Glad I answered the question. Is there any other questions? Are there any questions in this midterm where it would be a shame not to know? Nope. I think that applied to the last one. So what the hint is here is there was a very specific question in the review last night that I mentioned it would be a real shame if you guys did not know that specific question. So if you guys get a chance, I'd go recommend watching the review video last night, because it basically just gives away one of the questions on the exam. There isn't really any crazy one that I can think from this particular exam that you guys won't really know. It's pretty obvious out of this exam. Yeah. So if there's no other questions, I'll let you guys go. Time to go get dinner. Have a fun night. No Oilers game tonight, unfortunately, but oh well. I'll find something to do. Maybe go play some Animal Crossing or something like that. I know. I'm a loser, but that's okay. It's okay. Oh, now I got my saliva down my throat. Oops. All right, guys. You're free to go. Thank you guys so much for showing up. Oh, sorry. I got a question. For 2014, question 5, the compression test, we had the stress components in the stress tensor as positive. In 2015, we had them as negative. Is there a correct convention? When you're finding that confined pressure, when we're deriving it, we assume it's tension. But as you will see, depending on the Poissons ratio, it'll swap it automatically to negative. So it'll account for it based on the Poisson ratio. So I hope that answers your question. It's one of those things that if you derive it and follow the steps, it'll start to account for itself in the math. It isn't one of the things that we need to manually go swap. Yeah, it's a great question. Perfect. All right. So I will let you guys go. I will render the video right now, and then we'll have it hopefully uploaded by the end of the night. All right. Perfect. Thank you guys. You guys have yourselves a wonderful night. I will see you guys. Well, actually, I probably won't see you till after reading week. So you guys go have yourselves a wonderful reading week.